everybody. My name is Milena Tuimavave, and I'm a first-year transfer student studying aerospace and mechanical engineering.
Hello, my name is Matthew Pena. I'm a second-year aerospace engineering major.
Hello, my name is Blake Baxter. I'm a first-year mechanical engineering major.
And my name is Chris Apolito, and I'm a first-year transfer student studying aerospace and mechanical engineering, and we will be representing Structures, which is a team under the Space and Satellite Systems Club. Our goal today is to inform the world of the progress that Structures has completed so far. We will begin by introducing the main mission and explaining our role within the Space and Satellite Systems Club. From there, we will explain each sub-team within Structures and show their current progress. We will finalize this presentation by stating our goals for the remainder of the mission. Let's begin. Within the College of Engineering, there exists the Space and Satellite Systems Club, or SSS for short. Currently, the club is focused on mission REALOP, which stands for Remote Experimentation and Analysis of Low Orbit Phenomena, and is UC Davis's first ever undergraduate-based CubeSat mission. CubeSats are research-oriented satellites that have a volume unit of a U. Shown under Mission Overview, we see that CubeSats begin at 1 U, equivalent to 10 by 10 by 10 centimeter dimension, and multiply axially and laterally to form up to 6U configuration. Based on REALOP's mission requirements, we are designing a 2U CubeSat, or a 10 by 10 by 20 centimeter configuration. Mission REALOP is divided into 4 teams: Computer Science, Electrical, ADCS, and Structures. As mentioned before, we are here to represent the Structures team. Structures is in charge of creating the bus, which is a system that allows payload to operate in space, such as the frame and mounting gear. The goal of Structure is to standardize each design required for the bus by making it independent of the payload. Doing this will simplify mission repeatability and allow future UC Davis students to continue learning and exploring other aspects of space mission. So let's start with the frame design team. This team is responsible for designing the frame of the satellite. Because we are designing a 2U CubeSat, we must achieve a design no greater than 10 by 10 by 20 centimeter in dimension. Additionally, the total CubeSat mass should be under 3.6 kilograms. Through design iteration, we were able to successfully optimize our frame with a high internal volume of 1,625 cubic centimeters and low mass of 0.35 kilograms. Weight reduction strategies include minimum allowable wall thickness through analysis and minimizing mass cutouts with sufficient space to screw on the mounting brackets and the solar panels. Compared to our first version, we reduced the frame design by 11% while increasing the available volume for internal components by 4%. More importantly, we achieved a design that allows for effortless internal modifications. We did this by allowing any individual face of the CubeSat to come apart while maintaining structural integrity. So if a team wanted to change any internals of the already assembled and integrated satellite, they would be able to do so by quickly removing a few screws and gaining access to the inside, just like this. Shown on the bottom left is the evolution of the CubeSat frame. Most people overestimate the size of our CubeSat. And again, here is a life-size model of the frame to show you the true size for reference. We will now move on to Milena, who will discuss work from the subsystem integration team.
Thank you, Chris. The subsystem integration subteam is in charge of incorporating the designs of the other 3 teams participating in this mission. We report the internal volume of the frame and max dimensions available for each component. The components that we are focused on housing are 4 printed circuit boards, or PCBs for short, and the battery board that are being designed by the electrical team, and the coils and manufactured reaction wheel, or MRW, being designed by the ADCS team. Based on their designs, we decide where and how these components will be fixed on the frame of the CubeSat. To fix the battery board, coils, and MRW, we designed aluminum mounting brackets to constrain instruments and essential hardware into one location. The mounting brackets will be bolted to all 4 walls of the frame to reduce any shock the components may experience during launch. Due to the nature of the MRW, a top was also designed to keep it independent of the rest of the CubeSat so that it will not interfere with any of the other components in case it malfunctions. The mounting brackets have a standardized design that allow for quick and easy interchangeable parts and can be easily rescaled and reused for future missions. Traditional CubeSats use standoffs to hold the PCBs together. An example of this can be seen on the poster. Standoffs bolt all PCBs together, which makes access to individual boards difficult. In order to wire or access a single board, all boards would have to be disconnected. To bypass this problem and allow for easier accessibility, the Stackhouse was designed. It will be 3D printed using PEEK and will protect and isolate the PCBs from the rest of the CubeSat. The PCBs will be slid into each shelf of the Stackhouse and will be held together through its open face with 2 aluminum screws to avoid any rattling during launch that may cause damage. The Stackhouse will then be mounted to the frame of the CubeSat. The focus of the Stackhouse design was to allow for easier PCB access and ease of wiring, and similar to the mounting brackets, it can be easily rescaled to house more or less PCBs so it can be reused for future missions. And to explain how we have been testing and analyzing the integrity of our designs, we have Blake.
The test and analysis team concerns itself with the evaluation of our hardware's ability to withstand and operate within the harsh environment of space. By referring to data collected about common difficulties with low Earth orbit missions and data regarding launch conditions from our launch provider, the test and analysis team seeks to develop standardized methods and procedures to allow for the determination of our hardware's capabilities, to provide information on how to better improve them. The rising concern of our team has been the integrity of our satellite in response to the thermal environment of the mission. Thermal conditions during the mission are highly variable and dependent on factors such as orbital position, as well as conditions on Earth such as cloud cover, which can affect the Earth's albedo and thus how much solar radiation is reflected towards the satellite from the Earth, in addition to that already supplied from the Sun. In addition to internal radiation between components and infrared radiation from the Earth, data on the satellite's responses to great fluctuations in temperature is important due to the temperature of the mission fluctuating between very high and very low values. And these large range in temperatures of the satellite as it enters in and out of the shadow of the Earth more than a dozen times a day. Thus, we are currently working on developing and simulating a virtual model of the thermal situation using finite element analysis software such as Thermal Desktop. Being a relatively new program to the team, we are concerned with familiarizing ourselves with its capabilities as well as collecting data such as the thermal properties of our internal components to be used when we create the model in the program. With so many factors affecting thermal events, we are seeking appropriate ways to simplify the model so that we may develop physical and virtual tests representative of the actual worst-case scenario mission conditions. Such has prompted us to research appropriate means to simplify CubeSat geometry in regard to the finite element analysis environment by doing things like idealizing the model and appropriately discretizing and simplifying the model where it can be, as well as simplifying the thermal environment by determining the factors contributing only to the worst-case scenario thermal situations, so we can focus on accurately representing them in tests and simulations.
And with that, we'd like to thank you for making it this far into our poster and greatly appreciate your continuing desire to learn more about our work. Let's recap what our poster is about. We are a satellite team at UC Davis devoted to launching our first CubeSat into space. We have many dedicated and motivated members that work in known areas of interest to make this mission possible. For instance, we like to highlight the works of frame design who work to design the frame, system integration who try to puzzle in the many components of the CubeSat, and testing analysis who work to simulate the mission through software. On the right side of the poster, an example of a quarter's work of progress. The current model starts at the very bottom with the Stackhouse. Next is the mounting bracket with batteries. After is the coils. And on top of that is the reaction wheel with its mounting brackets. In all, this is leading up to the ultimate goal of mission repeatability. By making this template, future members of the Space and Satellite Systems Club will be able to use it for various applications and be able to take in missions quicker. With this ambitious goal looming around, there's still work to be done, and there's a lot to consider for future work. Though the most prominent goal is owning stronger skills in testing and analysis, trying to model the environment is no doubt a difficult task. This is why we would like to be able to create a far more accurate and advanced model of the CubeSat that takes more considerations into account that can be used to make micro adjustments to the main design, creating an all-in-one robust system that will be a product of many missions. Overall, we'd like to thank acknowledge Professor Robertson, Tim Keller of Vintopia, and of course the very leads Ricardo, Anna, and Jackson, along with many others in the background, because without any of them mentioned, none of this would be possible. And our last gratitude is to you, the viewer, for following along in our presentation. Thank you.